Okay, welcome back to the EE340. In the previous lecture, we talked about wave propagation in general lossy media. So in general, the electric field, or even the magnetic field, will have the following form. Let me assume that the wave is propagating along the z direction. And the electric field is along the x direction. So one factor is the attenuation factor here. And we see here, we'll see in this lecture that in some specific cases, there will be no attenuation. So remember, this is the general form, and we want to look into some simple cases. But before that, let's talk about plane waves. So in the previous problems, we always assumed that the wave the wave we have is a plane wave. And in that problem, in general, we assume that the electric, magnetic field, the magnetic field, and the direction of propagation are mutually orthogonal. In other words, we have the following formula. Where K is the direction of propagation. So such form is well known in the electromagnetic literature as transverse electromagnetic mode. So mode is a field configuration. So in this case, if the electric field, if I have this plane, let me assume this is the x-axis, this is the y-axis, and I have the z direction is pointing out of the peak. So the electric field will oscillate along this direction, for example. The magnetic field will oscillate along that direction, and the wave will propagate in a direction perpendicular to both fields, which is the positive z direction. So in order to characterize plane waves, those waves have equal phase front, equal phase wave fronts, and that wave front is perpendicular to the direction of propagation. So let me draw it here. If this is the direction of propagation, let me draw it in a better way. Over there, where I have enough space. Then I will have different planes here. So those planes, each plane will have something called constant phase front. What does that mean is, if I have exponential j omega t minus beta z, then at any point in this plane, this one is constant. For example, let's say like this one is A. We can go in details into plane waves, but this is beyond the scope of this lecture. The most important thing about plane waves is that they extend to infinity. However, in practice, this is not the case. We can assume that under two conditions, actually, under either one of two conditions. So the first one is, for example, in antenna engineering. We assume that the wave impinges upon the antenna is actually a plane wave, assuming that the source of this wave is in the far field of the antenna that receive that wave. Also, like in optics, where the wavelength is very small compared to the structure that impinges upon it. So we can fairly assume that we have plane waves. Now let's talk about the first special case. So the first one is lossless dielectric. In a lossless dielectric, sigma, the conductivity is very small, and it's much smaller than the product of the angular frequency with the relative permittivity. So we can assume the key term here is assume. We can assume that the conductivity is zero, and the permittivity is real. It's not complex. Remember, we used to have, for general lossy media, we used to have complex permittivity, and the permeability is also real. So this allows us to simplify a lot of things. The first one is the attenuation constant is zero here. The wave will not be attenuated, and the wave number, or the phase constant, is beta equals to omega times square root of mu epsilon. Also, we can simplify the wave velocity to the following. So it's always going to be omega divided by beta, and that's going to be 1 divided by square root of mu epsilon. And this one, as we'll see in a moment, that this is actually c, which is the speed of light. But since here mu relative is not, since here mu is mu r times mu naught, similarly epsilon is epsilon r times epsilon naught. So the wave velocity will be the speed of light divided by the square root of relative permittivity multiplied by the square root of relative permeability. An important character of plane wave propagation in lossy media is that in lossless medium or lossless dielectrics is that the intrinsic impedance is actually real, is not imaginary, and it's given by this formula. And again here, mu naught is eta naught is mu naught divided by epsilon naught, square root of mu naught divided by epsilon naught, which is the intrinsic impedance of free space. So now let's go to free space actually. So in free space, the relative permittivity is 1, the relative permeability is 1, and the conductivity is actually 0. It's not approximated to be 0, it's actually 0. So therefore, we have similar conditions. We have conditions similar to the case of lossless dielectric. However, here the wave velocity is actually the speed of light. So we just define the intrinsic impedance of free space, and it's 120 pi, or equivalently 377 ohms. So remembering this number will come in handy if you solve problems. The last case that we want to consider is actually a good conductor. So a conductor is good or is perfect if the following condition is satisfied. So the conductivity is much greater than the product of the angular frequency multiplied by the product of angular frequency with the permittivity of the medium. So for conductors, actually, the permittivity is actually the relative permittivity is really high. So in theory, if you have a perfect conductor, then this one should be infinite. This condition is equivalent to the ratio of the conductivity over the angular frequency multiplied by the permittivity is much greater than 1. So under this simplification, we can see here that if we substitute in the original formula, if we substitute these conditions in the original formula, we can conclude that alpha, the attenuation constant, is equal to beta, the phase constant, and they are equal to square root of pi times f, which is the frequency, permeability, the material permeability, and finally the conductivity. The wave velocity will be omega divided by beta. So taking beta from here, we conclude that the wave velocity is 2 times omega, square root of 2 times omega divided by mu times the conductivity. Also, the intrinsic impedance is very interesting here. We see here that the intrinsic impedance is complex, so it's not real, and the phase of that is always 45 degrees. So that means that the electric field leads the magnetic field always by 45 degrees. The last topic that I want to talk about is skin depth. So skin depth is a measure of the depth to which an electromagnetic wave can penetrate the medium. So remember from the previous video that if I have the electric field, if the magnitude of the electric field is E0 at the surface, then due to the fact that the electric field will be attenuated as it propagates, then all what I want in order to find the penetration depth, I want to find the exponent e to the power negative alpha z, such that this one is equal to exponent to the power negative 1. That means that the magnitude of the electric field at this point inside the material is actually almost 36% of the original magnitude. So mathematically, if we solve for it, we'll see that the penetration depth is 1 divided by the phase constant. And for a good conductor, we know alpha from the previous part here, and we can directly substitute. Also, we can use the skin depth to define actually a resistance, the surface resistance. So Rs is 1 divided by the product of sigma with the penetration depth. This is equivalent to saying that this is the resistance. Remember the DC resistance from electrostatic field was the following. So the DC resistance is actually, this one is equivalent to the DC resistance for a unit length, L equals to 1 meter, and a surface that is 1 times a surface area of 1 times the penetration depth. In other words, imagine that you have the following surface. So this one is the penetration depth, this is 1, and this is the length of 1 meter. Now, if I have a conductor with the width W, then I can bring those small components or small surfaces next to one another, and if it happens that the conductor has a length L, then each small component will extend to L, and it can continue until the width of these small components is, the total width is W, the thickness is delta, so the surface area for those is delta multiplied by W. And if I substitute it into that equation, to this equation, so I will get something called the AC resistance. So L sigma S in this case is delta W, and using the surface resistance we can simplify it to RS times L divided by W. So in the next video we'll solve some problems on wave propagation.